All right, today we're diving into something that feels a bit like a superpower for engineers and physicists, a seriously powerful tool for solving incredibly tough problems. It's called the Laplace Transform.
Think about it. You're staring down a beast of a differential equation, the kind that runs electrical circuits or describes how a bridge vibrates. Now, what if you could just wave a magic wand and poof, that calculus nightmare turns into a simple algebra problem you could probably solve in high school? Well, that's not magic. That's the Laplace Transform. The best way to think about this is like a special kind of machine. You take your hard problem, right, from our world, the time domain, and you feed it into this machine. It converts it into a much simpler algebra problem in what's called the S domain. You solve that easy problem, feed the answer back into the machine, and it translates it back into the real-world solution you were looking for. It's this awesome 6-step process that just works.
Okay, a machine that turns calculus into algebra? I know what you're thinking. This sounds way too good to be true. There has to be a catch, right? Does this thing work for everything, or are there some problems it just can't handle?
And you'd be right. It can fail. See, if you try to feed this machine certain functions, like 1 over t, or the ridiculously fast-growing e to the t squared, the whole thing just breaks. The math inside, this integral, it doesn't converge. It's like trying to find the final weight of something that just keeps getting heavier and heavier, forever. You never get an answer. So yeah, this machine has rules, and we have to play by them.
So let's pop the hood and look at the operating manual. To get this machine to work every single time, we need to understand its rules of engagement, and really, it all boils down to 2 key conditions.
First up, the function has to be what's called piecewise continuous. Now that sounds way more complicated than it is. All it means is that the function can have a few clean breaks or jumps, but it can't be shattered into an infinite number of tiny pieces. You know, think of a road with a few speed bumps, but it's not completely falling apart. The great news? Almost every function you'll encounter in the real world passes this test easily.
The second rule is that our function has to be of exponential order. In simple terms, this means our function can't just grow wildly, uncontrollably fast. There has to be some exponential function out there, like a super fast race car, that can eventually outrun it. It's basically a speed limit on how fast our function is allowed to head towards infinity.
So, let's look at some examples. Things like t squared, or any polynomial, no problem. They stay well within that speed limit. Sine and cosine, they just bounce back and forth, they're perfectly fine. But then you get these monsters, like e to the t squared. These guys grow so insanely fast that no exponential function can keep up. They blow right past the speed limit, and our machine just can't process them.
Okay, so if we followed these 2 rules, if our function is piecewise continuous and it's of exponential order, then we get something amazing. We get the manufacturer's promise, a guarantee that our machine is going to work.
And here it is, the official guarantee in all its mathematical glory. It says that if our function, f of t, meets those 2 conditions we just talked about, then its Laplace transform is guaranteed to exist, just as long as our new variable s is bigger than that growth rate constant c. This little theorem is the bedrock. It's why we can trust this whole process.
So what's the big deal with that c is greater than a part? Well, that is the secret sauce. That condition ensures that a different part of the Laplace formula, this decaying exponential, is strong enough to overpower the growth of our original function. It tames it, forces the math to settle down, and guarantees we get a real, finite answer. It's what makes the machine reliable.
All right, so we've run our problem through the machine, we've got our simple algebraic answer in the S domain, but we're not done, right? That's not the world we live in. We need to reverse the machine and get our answer back to reality, back to the time domain. And this reverse trip is called, you guessed it, the inverse Laplace transform. It's the final, crucial step that takes our neat little algebraic solution, f of s, and translates it back into the function of time, f of t, that actually describes what's happening in our physical system.
Now, you might be thinking, oh no, do we have to do another crazy integral to go backwards? And the answer is almost never. In practice, we just use a toolkit, basically a cheat sheet, a table of common transform pairs. It's like a mathematical Rosetta Stone. You find your answer, your f of s, on one side, and it tells you exactly what the original f of t was on the other. It's that simple.
So, let's try a really quick one. How would you find the inverse transform of 1 divided by s to the power of 5?
Easy.
We just look at our table, we find the pattern that looks like that, which is the t to the n rule. In our case, s is raised to n plus 1, which is 5, so n has to be 4. We plug that in, and the inverse is just t to the 4th divided by 4 factorial. 4 factorial is 24, so our answer is t to the 4th over 24. See? Simple.
But life isn't always that neat and tidy. What happens when your answer from the S domain doesn't perfectly match anything on our little table? Well, we need to pull out some more advanced tools. It's time to learn how to hack the inverse transform.
And our number one tool, our absolute best friend, is the linearity property. This is a total game changer. It basically says that if your function is made up of a bunch of pieces added or subtracted together, you can just take the inverse of each little piece separately and then stick them all back together at the end. It lets us break a big, scary problem into small, friendly ones.
Okay, armed with that, let's try something a little spicier. How would you find the inverse of this fraction? Minus 2s plus 6, all divided by s squared plus 4. Now, that is definitely not on our basic table.
We use linearity. We split that fraction into two. The first piece is minus 2s over s squared plus 4. The second piece is 6 over s squared plus 4. Now we look at our table. The first one looks almost like the cosine form. So we pull out the minus 2, and bam! We have minus 2 times the inverse of s over s squared plus 4, which is cosine of 2t. The second piece looks like the sine form, which needs a 2 on top. So we rewrite 6 as 3 times 2. Now we have 3 times the inverse of 2 over s squared plus 4, which is sine of 2t. Put it all together, our final answer is minus 2 cos 2t plus 3 sine 2t.
Okay, nice. But what about the really messy ones? What if you're faced with this beast, s squared plus 6s plus 9, divided by this whole mess of factors in the denominator? This looks awful, and linearity alone is not going to save us here.
For something like this, we bring out the big guns, the ultimate weapon in our arsenal, the partial fractions method. This isn't a trick, it's a systematic process. You take that one giant, ugly fraction and you mechanically break it down into a sum of much simpler, bite-sized fractions. Then you just have to solve for the new numerators, a, b, and c, and from there, each little piece is something you can find right on our table.
And after you run through that process, you solve for those constants, and you invert each simple little fraction. What do you get? Each piece turns into a simple exponential function. The final solution is just a sum of these three exponentials. We took something that looked hopelessly complex, and by following the rules, we broke it down into its fundamental, simple building blocks.
So you see, the Laplace transform isn't some unobtainable magic. It's a machine, a powerful one for sure, but it's a machine with rules, a toolkit, and a clear process. It's a method for turning the impossibly difficult into the totally manageable. So now that you know the rules of the machine, the real question is, what other complex systems out there could you simplify and solve?